When talking about Ethernet, we often think of the physical medium, the copper cable and its RJ45 connector. However, this cable is only the transmission infrastructure. In reality, Ethernet is a set of software protocols and hardware specifications standardized by the IEEE 802.3 standard. It is this standard that governs packet formatting, physical addressing, and media access. In this video, we will analyze the exact architecture of this technology. To understand Ethernet, it must be situated within the OSI reference model. Unlike other protocols, Ethernet is a hybrid technology that operates exclusively on the first two layers. At layer 1, physical, it specifies hardware characteristics, frequencies, and signal encoding. At layer 2, data link, it organizes the raw bit stream into structured and verified data blocks, Ethernet frames. The standard Ethernet frame follows a strict binary layout, where each field performs a precise algorithmic or hardware function from left to right. The frame begins with a 7-byte preamble, immediately followed by a 1-byte SFD, or start frame delimiter. The preamble emits a continuous alternating pattern of ones and zeros. This sequence stabilizes the receiving circuits and synchronizes the physical clock of the receiving network interface card with that of the transmitter. The SFD breaks this alternation by ending with 2 consecutive 1 bits. This serves as the strict marker indicating to the network controller that the next bit is the start of the payload data. Next come the 6 bytes of the destination MAC address. Ethernet positions the destination at the head of the frame to allow switches to read the identifier immediately and begin routing without waiting for the entire message to be received. The following 6 bytes constitute the source MAC address, representing the globally unique physical identifier of the transmitting network interface. The type field, or ether type, occupies 2 bytes. It identifies the upper layer protocol encapsulated within the payload. A value of 0x0800 indicates that the frame is carrying an IPv4 packet, while 0x86DD indicates IPv6. The payload is the central segment containing the useful data transferred from layer 3. Its size varies from 46 to 1500 bytes. The 802.3 standard imposes a minimum frame size. If the upper layer data is less than 46 bytes, the protocol automatically generates padding, a stuffing of 0 bits, to reach the required threshold, preventing the frame from being interpreted as a collision fragment. The frame concludes with a 4-byte FCS, or frame check sequence. This is an integrity check field based on the CRC32 mathematical algorithm. The transmitter calculates a cyclic polynomial over the entire frame and enters the result into this field. Upon reception, the same calculation is performed. Any discrepancy indicates bit corruption during physical transmission, leading to the immediate and systematic rejection of the frame by layer 2. To transit across the medium, these software bits must be converted into physical signals by layer 1 using a line coding method, such as Manchester encoding or MLT3, depending on the data rates. Historically, the 10-base-2 and 10-base-5 standards used coaxial cable. This medium featured a single copper conductor shared by all hosts. This physical architecture enforced half-duplex mode. Since the medium could only support one electrical signal at a time, any simultaneous transmission caused overlapping voltages, known as an electrical collision, rendering the frames unreadable. Technological evolution introduced twisted pair cables with RJ45 connectors. The 8 internal conductors are twisted in pairs to eliminate electromagnetic induction and crosstalk. This area of wires allows for the physical isolation of channels. In fast Ethernet, pair 1-2 is dedicated to transmission, TX, and pair 3-6 to reception, RX. Thanks to these independent bidirectional channels, Ethernet eliminates collisions and operates in full duplex mode. Increasing the sampling frequency and reinforcing the shielding, as seen in S/FTP structures, currently allows for data rates ranging from 10 to 40 gigabits per second over copper links limited to 100 meters. For interbuilding or backbone links, the Ethernet standard integrates fiber optic media. The signal is no longer electrical, but photonic, modulated by diodes or lasers, eliminating attenuation and distance constraints. Now that we have the frames and the cables, how does the hardware orchestrate all of this? This is where the historical duel between the hub and the switch takes place. The hub is a device operating strictly at layer 1. It has no knowledge of the frame structure. When an electrical signal appears on a port, The hub behaves as a simple multi-port repeater. It amplifies the signal and broadcasts it across all other ports, saturating bandwidth and creating a single collision domain. The switch is an intelligent Layer 2 device. Upon receiving the first few bytes, it extracts the source MAC address to populate its switching table, known as the CAM table. It then analyzes the destination MAC address, consults its table, and switches the frame exclusively to the physical port where the target host is located. This microsegmentation isolates traffic and allows for the maximum exploitation of full duplex mode, completely eradicating collision domains. The Ethernet architecture demonstrates how a hardware and software standard defined by IEEE 802.3 successfully evolved from the physical layer to the data link layer to adapt to modern throughput demands. If this technical analysis of network protocols was helpful to you, subscribe to the channel for upcoming engineering modules, and let us know in the comments which technologies you want to analyze next. See you soon!